introduce you. Hello, everyone. Welcome to MACSMIN 2025. It's a great pleasure to introduce Isaac Sugden, the team leader in computational data science, right at the Cambridge Crystallographic Data Center, who will talk about making use of the CSD, Cambridge Structural Database, to study metal organic complexes. So we are now back to applications from theoretical graphs in the previous talk. Over to you, Isaac, please.
Perfect. Thank you, Vitaly, and thank you for the invitation. Yes, I don't know 100% the mix of the audience for today. I enjoyed the last talk. This one will be, as Vitaly says, a little bit more applied science and a bit more sort of, well, less thorough mathematical, essentially. What I'm presenting here is some of the work that my colleague Chris Kingsbury has been working on over the last year, some data analysis and some prototypes that he's generated. He wasn't able to speak today. He's currently in New Zealand and it's bedtime for him. But I'll be talking through the work. If you have any questions, I hope I'm able to answer them, but there is a chance that I'll have to defer some of the questions. So, as Vitaly said, we're making use of the Cambridge Structural Database to study metal organic complexes. We're going to be looking at coordination chemistry, semiconductors, MOFs. So this is metal organic frameworks or coordination polymers, as they used to be referred to as, or organometallic. So crystal structures with metal and organic components that aren't in a framework in the same way. This slide is just introducing to those who aren't aware of the CCDC, what we do. So CCDC is a not-for-profit, is a registered charity with a charitable objective of advancement of chemistry and crystallography for the public benefit through providing high-quality information services and software. And this year celebrated its 60th birthday. So if you see the image on the right there in the top left, the point of the CSD is to curate this international repository of 3D crystal structures, and that's the CSD. We also perform collaborative research and do knowledge-based services, and we provide scientific software, and that's going to be a lot of the basis of this talk, and also perform training, education, and outreach. I was at Liverpool at the start of the year for a short sort of training workshop. If we look at the CSD, so this is a Venn diagram showing how the CSD interacts and overlaps with other structural databases. So there's 1.3 million structures in the CSD. I think there's going to be a couple of talks focused on protein crystallography during the course of this conference, and the PDB has some overlap with the CSD. So, for instance, there's 230,000 structures. It makes use of Mogul, which is a CCDC piece of scientific software, and there's ligand linking between structures in the CSD and ligands or drugs in the protein data bank. The ICSD in the top right, that's the inorganic crystal structure databases that's led from Fitz Karlsruhe. There is, again, some overlap of structures there, and if you've been paying attention to the Kerlin Group's present publications this year, there was a very good paper that looked at using the PDD methods to analyze the overlap between those two databases, which I do recommend. There is joint access to those two databases. So if you log into the web service for the CCDC access structures, you're able to search across CSD and ICSD, which our users have been requesting for a little while. And then in the bottom right is the ICDD. So I think I included this because I've presented these slides when I've been discussing Autofidel, our powder diffraction piece of software. ICDD is the International Center of Diffraction Data, so it hosts PXRD patterns for common chemicals, but as of a couple of years ago, they're also hosting simulated PXRD patterns from the 3D structures that are in the CSD, and I think that's been a useful collaboration. If we take a look into the 6.0 release, which was a couple of months ago now, we're up to 1,371,000 crystal structures, and because Chris produced these slides, he's included the prime factors of that number. And more than half of the CSD does include crystal structures that include metals, and so it's worth discussing that the CCDC's main funders and most of the research that's published on using the CSD is a little bit more focused on the pharmaceutical or agrochemical side of crystallography. But there is a wealth of data in the other half of the CSD. And inorganic chemistry is still the most popular journal for depositing crystal structures in the CSD. So this pie chart on the right, I don't know if you can necessarily refer to it as a pie chart actually. This chart on the right anyway shows the number of unique metals in the crystal structures. So we have 92,000 with copper in them, and only one with an actinide because actinium, because that doesn't last long enough to be measured as a rule. Okay, so another look at the CSD. So it's a database of all the published organic and metal organic crystal structures. As I've said, about more than half is metal organic. The majority of it is non-polymeric, but there is polymeric materials, and that includes MOFs. There are over half a single component, but there's also multi-component, so salts and co-crystals and so on. And if you look at the bottom right there, some linking to other databases has been a focus of CCDC for a few years now. So linking to the drug bank and the drug-like data sets, as well as PubChem and ChemSpider, has been requested by users, and I think it really adds to all those databases to be able to search across them. So in this talk, I'm going to talk a little bit about topology and dimensionality. The previous talk gave us a lot of background on graphs, connections, nodes, edges, and so on. I'm not going to be going into the same level of detail, but hopefully retain some interest. Coordination info, so interactions between metals and ligands, and some basic metal steric descriptors, so including the cone angles that are induced by a ligand on a metal. There'll be a slide on semiconductor, data calculated fields, and aromatic interactions. Obviously, there's quite a lot to cover here, so we won't be going into too much detail, but hopefully it's a possibility to start some collaborations. So the motivation for studying topology here, we've got a cartoon of some Lego blocks. Crystals are held together by forces, and the network that these form is a fundamental property. So as an analogy, these Lego bricks are all equal energy structures because they satisfy the same inter-brick interactions, and they have the same conformation and density, but the difference between them is that is the connectivity. So you can see if you have, and this does occur in crystal structures, if you have the same molecule crystallizing in two different crystal structures, one of which has a more interdigitated and strong linking between molecules and a well-defined topology, then it's likely to have different physical properties to as the same polymorph with a different topology, a different set of connections. And rationalizing those interactions is a big motivation for instance, people working in the pharmaceutical industry, because it's the way that they seek to control how molecules crystallize in order to be able to understand their physical properties, like solubility or stability of the drug they're hoping to make into a tablet to bring to market. You know, the hygroscopicity and how much water a crystal will take up is also an important fundamental property that's controlled by topology. So we've taken, sorry, apologies, an approach based on that of the RCSR for representing topologies. If we take an infinite network, and it can be represented by a vertex symbol, so encoding nodes, edges, cycles, and degeneracy. If you take this square lattice as an example, and you look at the central node, it's 4 connected. You can form 4 circuits involving 4 other nodes, and it can form 2 8 circuits, including so 2 8 circuits where there's 8 nodes able to link back to the original node. So in these diagrams, each circle represents an individual molecule, so essentially the centroid of the molecule, and the connections represent intermolecular bonding. So that can either be hydrogen bonds, it can be aromatic interactions, or it could be metal to organic ligand bond in, let's say, a moth. And being able to have this sort of unified representation of topology is useful. There are other ways to represent topology, obviously. But if we go a bit further with this, and we look at the cumulative total number of nodes in a shell of 10 connections, that's a common check when 2 networks have the same vertex symbol. So again, looking at this square lattice, which is defined in the RCSR as layers SQL, is one of the most common topologies that is counted in small drug-like molecules. So we've applied this tool to look at this single component drug subset, and 9% of those the structures in that drug subset have this topology. As well as thanking the previous speaker for the nodes and edges introduction, I have noted that the speaker that follows me will also go into some detail about rods and layers and so on. And so I won't go into too much detail here, but we're in a unified theme. In terms of dimensionality, then generally the collection can be defined as one of these classes: abstract points. So a 0D structure is given in the top left there, where there is only one connection between 2 nodes, and it terminates there. You have 1D examples where you get ribbons, lines, or rods. 2D examples like wallpaper and layer groups, and then finally you have topology with 3D, which are referred to as place groups. So how would you make use of a tool that assigns topology? This is an example analysis. So quite a simple molecule here, benzene 1,3,5 tricarboxylic acid. It's the image is on the top left, and this ref code in the bottom left is how you might is assignation in the CSD. So in the center image, you have an abstracted topology from this crystal structure. You can see the pink lines; those are hydrogen bonds between molecules in this crystal structure, and unsurprisingly, given the molecule shape, you set up this sort of hexagonal topology, which is a layer, or and is given the assignment layers HCB, honeycomb. The blue spheres, then you can see a helix being set up going between layers in the 3rd dimension, and that's because of the assignation of aromatic interactions. So these are offset stacks of benzene units sitting at offset from the molecule below it, and you can see that it sets up a helix rather, going through that dimension. And so the tool that I'm discussing here can give you information, hydrogen bonding and aromatic interactions, but also the combined topology from looking at how those intermolecular interactions propagate through the lattice, and you can get a 3rd assignation. If you want to make use of this tool, from this year, you could just go to, when you open Mercury, you go to Python API, prototypes and topology, and you can click on combine topology and it will run it on the structure that you have open in Mercury. It also works through the command line, and it's anticipated that people want to do some like bulk data analysis on databases using tools like this. So the command line is where we expect to see most usage. Any issues? This is a prototype tool, so it's not been through the same sort of software developers applying unit tests and so on. It's written by scientists. So any issues, do get in touch with myself or Chris. This topology and assignation tool is part of an auto-generated MOF report or health check. So it presents important information and how one can search throughout the CSD for similar assignations. It was made using the Python API and is available on request and is on CCDC open source. We intend this will be on CCDC open source GitHub shortly. And we have had discussions with users on making use of this tool for standardizing data for survey in terms of using it as an input to AI and ML models. So you can see the sort of information you get out of running a MOF report there, ligands and metals and so on. If you want to make use of that, then you go to the open source when it's uploaded, GitHub, and then you paste the script into your Mercury scripts folders or use it through the command line. There's actually quite a lot of quite useful tools on that GitHub that I don't know is well known amongst our users who often make use of the software for one very specific task. But there's quite a lot of very useful stuff in there, as I say. So moving on then, if we explore the MOF subset with the topology tool run on it, there's 27,000 structures in that subset. So hopefully the majority of you are aware of what a MOF is. But this is this second class of materials where you have a metal node with connecting ligands. About half of them are either square lattice or honeycomb topologies. It's quite easy to bulk assign a lot of them. And when you're discussing MOFs and their characterization, the ways in which MOFs are used is often in terms of gas uptake and catalysis. So knowing how gas or solvent is able to penetrate through a crystal structure is obviously a property that's defined by topology. So 9,000 of them, of these crystal nets, have no assignment in the RCSR, which is the database we're making use of to assign these topologies. So there's a few that we've defined ourselves, double layer grid or waffle fries topologies that can't be flattened, but the majority of these are in RCSR. So I'll pause there and just mention that we're now moving on to looking at tools that are able to investigate metal complexes. So when we're dealing with metal organic crystal structures, we have usually a metal atom that's surrounded by organic components. These are called ligands. It's a different definition to the protein ligand, which is where the method of action is the same. Ligand has the same root word in terms of etymology as ligature and ligament. It's talking about binding. So a drug will work by binding into a protein, and these organic ligands bind to the metal. And they must fit around the metal to bind. And when people are performing catalysis or they're designing catalysts, they need to understand which ligand to use to get the catalytic property they're interested in. So having an idea of how the ligand will fit around similar metals is useful. So we have a tool then that calculates Thom's cone, which is the top left, and it shows a very basic idea of how much space one ligand will take around a metal center. The top right is a multi-pole cone that allows deformation outside of the plane. So the multi-pole cone should be giving you a much better idea of how much space is available around the metal once that specific ligand binds. So you can see the numbers calculated there as 67%. You know, there's still a large amount of space available for other ligands to approach that metal. It also gives buried volume, which is based upon points in space around the metal and surface angle. And all of these are useful descriptors for describing what you expect a metal to, how a metal would interact with a third party then in terms of forming catalysis. An example of how you might use these is, for instance, in propylene catalysts. So cone angles for zirconium with these 3 different types of aromatic interactions in a pincering the zirconium with its 2 chlorines. You see the multipole cone is essentially occupying almost the same volume across those top 3. And then as you introduce different bonding scenarios around the benzene units, you can see the ligand starts taking up more space around the metal, and you get this higher multipole cone example. So a good steric descriptor should sum up to 100%, and it should give some information about enforced conformation, because if we're forcing a metal to take up a certain conformation, then that will have an impact on its electronic properties, and following that, its catalytic properties. The descriptor should correlate well with experimental information and should be easy to calculate and reliable. And I've been focusing on how calculating these steric descriptors is useful in catalysis, but it's also something that turns up in magnetism, nanoparticle formation, and organic sterics, and that we aim to publish that shortly. A further example of using these steric descriptions is in BiNAP. So this is binaphthalene, and this is a ligand that can induce chirality. It's a common ligand in disymmetric catalysis, where the catalytic step introduces a chiral center. The reason being because in BiNAP you have 2 naphthalene units bonded, and because the aromatic units are then forced because of sterics to be at 90 degrees to one another, that starts to introduce a helix, and the helices have chirality. Fusely pasta can't be superimposed on a different type of fusely pasta. And so once you introduce that type of ligand, you can then start controlling the catalytic ratio of chiral products. So the BiNAP ligand is common in crystal structures. There's 581 examples. And if you look at the picture on the bottom right, you can see that in the upper right and the lower, in the top right, you have a projection of the phenol group into the upper right and lower left quadrant, which pincers and induces that chirality. And if you see in the bottom right in the image, the cone of ruthenium BiNAP complexes, of which there's 76 examples, and you can clearly see a P and M are distinguishable. So these 2 plots show that the different isomers of these complexes. When we're performing disymmetric catalysis, I think I've alluded to this already. What's needed is a misalignment between the steric and electronic multipole. So what this is saying is that the ligands should be inducing electron density along directions to the metal center that destabilized some molecular orbital metals orbitals and stabilize others. So you get this sort of frustrated metal that doesn't quite have it doesn't have a perfect setup of electronic orbitals given the steric interaction with the ligand, and so it's able then to perform catalysis because it's sort of able to accept other molecules as reactants because it's in a frustrated state. So if you're looking at disymmetric catalysis, you also require a tight binding between ligands and metals, and all mean surfaces are in contact. The electronic states I've mentioned are conducive, and that aromatic interactions are common. So you can see in this image on the right, we have a few lines drawn between aromatic centers in the ligand, which is controlling the bind to the metal. A question is often asked is that, is crystal conformation a strong indicator of conformation in solution? So a lot of the time these organometallics structures are used in heterogeneous catalysis, so they're dissolved in a medium with the reactants, which means they might be in a slightly different conformation than they are in the crystal, but the crystal structures are a representative sample of lowest energy conformations of that complex. Excuse me. So if we now look at how we have the same ligand and with different metals and different other ligands, what's the range and spread of multipole percentage, this steric descriptor. If we look at triphenylphosphine as the example ligand for a metal complex, you can see as you progress across the periodic table, you start to see trends in how much multipole percentages is available with the same ligand. And you can see going across these transition metals, you get a column where there is largest multipole percentage for nickel and gold, and then at the extreme edges of the transition metal section of the periodic table, you have much lower percentages. And as I was indicating earlier, that's due to the different electronic orbitals at the metals in each of these centers. So this is the same ligand across 22,000 or nearly 23,000 crystal structures. So it's a reasonable data set to start making these assignments with. But you can see there is quite a lot of spread of results, certainly for silver and ruthenium. We've also recently performed a project in collaboration with Alessandro Trossi and Tahare Nematarian. So the work was done at Liverpool when Tahare was there for her PhD and postdoc. So what this is a data set that was calculated for structures within CSD. The molecules were extracted from their crystal structures, and then semiconductor relevant properties were calculated using DFT methods. There's a set of papers to go into more detail of the methods that we used. It's quite high-end calculations. Having generated that data set, you can now search it as part of the CSD. So if you take the example of Anari here, we have a small prototype script that again is hosted on CCDC open source, and if you run it on the molecule that you have open in Mercury, you can get this sort of analysis that's on the right here produced. So the most obvious calculated property that's relevant for semiconductors is the HOMO-LUMO gap. So if the energy difference between the highest occupied molecular orbital and the lowest unoccupied molecular orbital is in the range of visible light, then that suggests that you have a potential organic solar cell component. It's able to absorb light in that region. Transfer integral then is giving you an indication of if it is able to have an excited electron because of absorbing visible light, is it able to then transfer that excitation to the next molecule along? Is it able to propagate the excitation? And there's a few other properties that are more focused on what type of semiconductor it can perform, but it's useful to have this tool that shows you within the context of this, I think it's 40,000 calculated properties, where your molecule sits amongst that large database. Some more properties we've added recently is voids. So if you run the void analysis tool within Mercury, you can generate this sort of analysis, which is on the right. So this is DAXMIC. This is a osteoporosis drug co-crystal, and you can see it's got small volume with a small pore emitting diameter. And if you look on the left, you can see both the types of pores there. And that means that nothing is going to flow through this material because the pores are essentially zero-dimensional. But you can then start making predictions of what would fit inside that, and so this 185 cubic angstrom is about 2 acetonitrile molecules, and you can see that you can then tell that this is then a solvated structure where the solvent was removed. Sorry, did I skip one? There we are. So other things you would do with a void analysis tool is to look at large voids. So for instance, in coordination cages like Adusor. So this is a large volume, medium pore diameter. So after deleting the compound in a cage, we can look at the maximum pore diameter, which is 13.59. That's about the size of a ruthenium complex. But the 5.7 angstrom pore limiting diameter is too small for that complex to get out of the cage. And so you can start making decisions on what material is going to be useful for which application. And then finally, we've got an example of a very large molecule, a large void crystal, I should say. So this has a large diameter and actually quite a huge volume. And in fact, if you look at the system density, you can see that if this crystal structure didn't just absorb water, it would be lighter than water and would float on it. And so this sort of system where you have very large pores propagating through the system, you can then make predictions on what application it would be useful for and potentially able to take up a large amount of gas, for instance, in the carbon capture industry. The final part of my talk, I'm going to look at, sorry, I don't have, I'm not able to see time actually, so 10:36, all right, we're doing all right. So is to look at aromatic interactions in the database. So when you have two aromatic units, so benzene is a good example, they tend to interact with each other either in an offset stack arrangement, which I've alluded to earlier, where two planar molecules sit above each other in parallel but offset centroids. You also have the chance of a T-shape where the two benzene planes are approaching 90 degrees, and a proton from the approaching benzene unit is then placed into the electron density of the accepting benzene, or direct strapped interactions here, which are much less common. So when these shapes appear, they're important structural features and contribute up to 20 kilojoules per mole of intermolecular interaction in normal rings. The image is showing you where the best interaction zones are. Yes, well, a few different rings are able to be analysed with this tool. So the way that we've designed this tool to analyze aromatic interactions is to simplify a coordinate system to reduce the degrees of freedom, and then we analyze those independent variables against chemistry, symmetry, and AA1 score and kernel density estimate. So AA1 score is just machine learned potential that is trained on DFT calculations for two molecules in the gas phase approaching one another. So a good AA1 score suggests that it's quite a low energy interaction, whereas kernel density estimation is looking at how often those types of interactions appear in the CSD. And so you can there's a correlation between those two values, and you can see then that their aromatic interactions are important. We can see from AA1 that they have they're low energy, and we can see from the KDE that they turn up in nature an awful lot. The tool will then export the information back to a visualizer or a command line or notebook, and users have found those three ways to interact quite useful. I won't go into too much detail about the coordinate system. Just A1 is defining the interplane angle. Z is how far away the two centroids are in that key coordinate away from the accepting benzene's plane, and then X and Y are the how different the two molecules' centroids are within the plane of the accepting molecule. And then A3 is if you have a substituent on the donating aromatic unit, then how where the substituent is pointing, so rotating on its own axis. If we plot the all of the interactions from molecules within the CSD where there is an interaction between aromatic units, if we plot A1 against Z and then highlight the results for that AA1 score, so again 10 is a good low energy interaction, you see this sort of almost sinusoidal shape where you have a lower Z value, so closer centroids associated with a low A1 angle, so not so the planes are almost parallel, and that is very descriptive of an offset stack interaction. And then the graph moves through higher Z values and higher A1 scores until you get this this interaction that's defined in the top right, which is T-shaped, where you have centroid slightly further away and the interplane angle being closer to 90. So this is our rationalization for a geometric model for benzene-benzene pair interaction, and all of the data here has come from the best R factor list, which is 500,000 ring pairs. If you look at the graph in the top right, this is for interactions where A1 score, so the interplane angle is greater than 30 degrees, so it's more T-shaped like, and then we rotate around A3, so that's the donating molecule's own axis, and you can see it's sort of a sawtooth mode where the molecules move away a little bit as the proton moves out of the accepting molecule's electron density, and then move back in as it keeps rotating around its axis. And so this is a six-fold interaction that's showing you the protons like to be placed in the electron density of the next benzene unit. If we instead focus on where A1 is less than 30 degrees, so this is closer to being an offset stack interaction, you get this sort of donut shape where you have a hole in the middle at XY equals 0, which is telling you they don't like to sit directly on top of each other, unless you have the case where it's hexafluorobenzene and its electron density is very much different to a normal benzene. In view of time, I won't go into too much detail here, but you can apply the same analysis for lots of different types of interactions. So benzene is what we've been looking at so far, but also benzene, pyridine, thiophene, pyrrole, and furan. And you can perform the same analysis regardless of what components are in the rings. This sort of aromatic interaction survives the substitution of heteroatoms. Excuse me. So one final piece of information you might take from that large data set is the substituent directing influence. So looking at T-shaped interactions here. And so if you remember from, I don't know, if the first year undergraduate chemistry, we have toluene. So this is a benzene with a methyl group replacing one of the protons, and that tends to be also para-directing in terms of how it reacts, because there is electron density then pushed to the proton directly next to where the methane is, and directly opposite, so that's also in para. And you can see a very small bias of 7% for the case of toluene, which is probably not really that statistically significant. For chlorobenzene, so this is an electron withdrawing group, it should be meta-directing, and you can see a slight bias of 7% there. The same with nitrobenzene, which is a much stronger electron withdrawing group, but only a 4% bias. When you get sort of very large substituents like R3Si, you see a much more significant bias towards the meta position. And so that's suggesting to us that steric interactions are quite an important consideration there. Having gone through all that larger data set analysis, what we might like to do is use this tool to start analyzing polymorphs for instance, drugs. So this comes back to this health check consideration that is that pharmaceutical companies will be making when they're trying to bring a drug to market. So if they have one polymorphic form, they would like to use some digital tools to be able to understand, are all of the interactions within this molecule, within this crystal structure satisfied? If not, then we might need to start thinking about a later polymorph arriving with more stable interactions, more interactions satisfied. So it's useful to have tools like these to perform the analysis of the initial molecule. So if we look at pentoxifylline, this is a common muscle relactant, and this was chosen because it has polymorphs. Those polymorphs have got melting points associated with them, which is a good proxy for stability, but doesn't include any amino or alcoholic groups, so we can exclude hydrogen bonding. It exhibits two known polymorphs in the solid state, so there's one metastable monoclinic form and one stable triclinic P-1 form. When we apply when we run aromatics analyzer on these two polymorphs, what we can see is for the JAG-K, which is excuse me, so if you look on the far right, melting point is 378 to 379. Compare that to on the right of the image, you have a melting point of 365K. So a higher melting point suggests more stability. The more stable compound on the left has only one aromatic interaction being expressed, but that interaction is propagated through essentially a line topology. Each molecule is interacting with by one interaction with the molecule next to it. If you instead look at the polymorph on the right, we have two aromatic interactions, well, essentially 1.5 interactions happening between each molecule and its neighbor. However, those interactions are essentially point interactions, if we remember the topologies from the start of this talk. And so even though it's got more aromatic interactions because they're not propagated through the system, it's not holding the whole crystal together strongly in the same way, which is how we can get to this lower melting point and an R-cyanation of a less stable structure. Again, if we take a subset of structures where we have polymorphs derived from the melt, which are likely to be the kinetic forms and less stable, and then also a stable polymorph, and we apply the same aromatics analyzer to them, we can see that there's several where there's stronger aromatic interactions from the melt. There's a few where there's essentially the same interaction, and then there's only 4 with the more stable polymorph having stronger aromatics interactions in them. So in this way, aromatics could be aromatic interactions could be an indicator of instability, in fact. And what that's driving at is that these molecules haven't had hydrogen bonds excluded from them, so they are able to make hydrogen bonding interactions which are more stable. So aromatic interactions form quicker, so they can lead you down a kinetic polymorph path. So this is a very useful reference paper from the Crystallographic group. I think I will skip over the analysis here, but it was reinforcing the work that was done in this to produce the polytype. So this not polytype, sorry, this prototype. So it's a narrative tool, and it's showing that interactions appear about once per ring or 2 per molecule. The interactions where there's a distance of less than 1 angstrom from ideal shows you it's a good aromatics interaction. There's a range that needs interpreting, and then further than 1.6 angstroms from the ideal position, then that aromatic interaction is essentially irrelevant. As a strong substitution has a strong effect on type and directionality, and we saw from the pentoxaphylline and other examples that good aromatics can make for bad polymorphs, and that we can have networks and dimensionality help us understand and explain structural motifs. So in conclusion, we've seen that the CSD data and tools can help to contextualize, analyze, and visualize difficult crystals and concepts. We're able to, search is a good place to start with any hypothesis, and it's sometimes easier than going in the lab. And all of the properties that we've discussed today, there is pre-computed databases, and you are able to search on those properties. Topology is useful in understanding how something is connected together. I didn't really cover octahedral complexes due to time. But aromatics can show us how to study chemistry from a database. So contact ccdc.cam.ac.uk for issues, and myself and Chris if you would be interested in doing collaboration along these lines. I'm going to stop sharing if that's all right, Vitaly.
Isaac, you could keep the slides, but let us first thank you for the talk.
Perfect. Yeah, I'll keep the slides there. I saw a comment, a